In this video, we discuss the notion of subgroup of a group, and we provide a lot of important examples of subgroups, which will be kind of used throughout the next few videos as well. So what is a subgroup? A subgroup, so we'll say let G be a group and H be a subset of G. We call H a subgroup of G if H itself is a group under the same operation as G. So what does that mean? A subgroup is just a smaller group sitting inside of a bigger group. That's the way to think about this. So what are some examples? Well, the first example is if G is any group, I could take H to be the set containing just the identity. This is always a subgroup of G, and it's called the trivial subgroup. Why is this the case? So why is it closed? Well, E times E is equal to E. So it's closed under multiplication. We know that the multiplication is associative because the associativity is inherited from G. We know that the identity is in there because E is in there. And we know that every element of H has an inverse. Namely, E has itself as an inverse because E times E is equal to E. So this is called the trivial subgroup. For any group G, if I take the set just containing the identity, I get a subgroup. Okay, so what are some more interesting examples? One interesting example is the set of positive real numbers. So one thing to recall is that in the last video, we talked about this group called, or I guess 2 videos ago, we talked about this group called R star. So these are the non-zero reals. And we talked about it being a group under multiplication. So it turns out that the positive reals, I'll call it R greater than 0, is a subgroup of R star. So let's think about this. Why is it closed? Well, if I multiply any two positive reals, I get a positive real. So it's closed. I know that 1 is a positive real number, so the identity is in there. I know that multiplication is associative. That's always inherited from the bigger group. And then finally, inverses. I know that if A is a positive real, then 1 over A is the inverse of A, is a positive real. So 1 over A is in my set as well. So I have inverses, closure, identity, and associativity. Those all hold. Okay, what's another example? Z is a subgroup of Q under addition. We already know that Z and Q share the same operation of addition, and that Z is a subset of Q. And we know that Z is a group because any ring we showed was a group under addition. Okay, so these are our first examples. Okay, so let's look at a few more examples. One example will be the set of rotations in R3, rather in D3. So D3, remember this was the dihedral group of order 6. There's 6 elements in there. And this is the symmetries of the triangle. And it was of an equilateral triangle. And the thing to remember is we had 3 rotations. We had a 0-degree rotation, a 120-degree rotation, and a 240-degree rotation. And one thing to notice is that if I compose any 2 rotations, I get another rotation. I notice that R0 is my identity element. It was my identity element of D3. I notice that I have associativity because D3 had associativity, and I noticed that I have inverses because R0 composed with R0 is R0, and R120 composed with R240. That's the same as a 0-degree rotation. So here's an example of a subgroup. Another thing we can consider is the group U of Z mod 16. So remember, these are the units in Z mod 16 under multiplication, and these are all the elements of Z mod 16 that are relatively prime to 16. So what subgroup are we going to consider? I'll consider the set containing just 1 and 7. And I'll check that this is a subgroup. So let's check closure. So let's check that our multiplication always lands inside of H. So if I do 1 times 7, I get 7. That's inside of H. 7 times 1 is 7. That's inside of H. 1 times 1 is 1. That's inside of H. And 7 times 7 is 1. So that's inside of H. So I see that I have closure. I know that I inherit associativity from G. I know that I have the identity because 1 is the identity. And I know that I have inverses because 1 times 1 is 1, so 1 is its own inverse, and 7 times 7 is 1, so 7 is its own inverse. So this is an example of a subgroup. And the final example that I'll mention is that Dn is a subgroup of Sn. If we think about our group Dn, these are the symmetries of a regular n-gon. We note that what we're doing is we're permuting the corners, right? So if we label the corners 1 through n, every element of Dn is some sort of permutation of those elements 1 through n, and Sn is the set of all possible permutations of the elements 1 through n. And the idea here is that Dn has 2n elements, and Sn actually has n factorial elements. So we'll talk about this a little bit more later on when we do a more in-depth video about Sn. So usually, unless n is equal to 3, Dn is going to be a proper subgroup of Sn. So Finally, one last thing I'd like to point out is there's oftentimes a notation used for subgroups. A lot of times if you want to say H is a subgroup of G, instead of writing the words out, people will just simply write H is less than or equal to G. So we'll use this notation from time to time. Okay, so the first question to now ask is, how do I easily identify a subgroup? Well, what we can do is we can only check a few of the axioms. So we have a theorem that says the following. I'll say, let G be a group and let H be a non-empty subset of G. We'll show that H is a subgroup of G if and only if, for all A and B and H, we have that closure holds and that inverses are contained inside of H. So let's go ahead and prove this. The forward direction is trivial. The forward direction just follows by definition of a subgroup. So if H is a subgroup of G, then we automatically have closure inside of H, and we automatically have that inverses exist inside of H. So this is just true by definition of subgroup. So the backwards direction is more interesting. So I'll say, suppose, well, what do we have? We have that AB is an H for all A and B and H, and A inverse is an H for all A and H. Well, what do we have? We have closure. This holds because, well, closure is just our first assumption, right? So this is closure. We have inverses because inverses are just our second assumption. We have associativity because this is inherited from G. So this is inherited. It's the same operation. I'm just working with a subset of G. So this is inherited from G. And so the only thing we need to check is the identity. Right? We need to show that E is an element of H. We have all the other axioms. So let's check this. So I know that if A is an H, then by our inverse assumption, I know that A inverse is an H. Okay, well, then by our closure assumption, I know that A times A inverse is an H, and we know that E is equal to A times A inverse. So we get that E, which is equal to A times A inverse, is an element of H. And so we've checked that identity holds as well. So we have associativity, we have identity, and so we've shown that H is a subgroup of G. Okay, so let's use this theorem for some examples. Okay, so for our first example, we'll do an example with matrices. So remember, GL2R is the group of 2x2 invertible matrices whose entries are real numbers under the operation of matrix multiplication. We know that this is a group. And what we're going to show is that the set of matrices H of this form is a subgroup of GL2R. Okay, so let's prove this. The first thing we notice is that H is not empty, right? The theorem above tells us we have to check that H is not empty, since we can produce an element of H. I don't know, 1101 is an element of H. So great, this is not empty. Now let's check closure and let's check inverses. So closure, we know that we can say, well, let 1A01 and 1B01 be elements of H. Then let's multiply them together and check that we get an element of H back. 1A01 times 1B01. If we multiply these matrices together, we get 1A plus B, 0, 1. And I have a matrix of the right form. And I notice that if A and B are real numbers, then so is A plus B. So I have 1, a real number, 0, 1. So this is an element of H. Okay, so I have closure. And now let's check inverses. So one thing I know is that if 1A01 is an element of H, then the inverse of this matrix, 1A01, its inverse, is 1 negative A01. And this is an element of H. And I can check that this works, right? I can check that 1A01 times 1 negative A01 is the identity matrix, so 1001. And that 1 minus A01 times 1A01 is also the identity matrix. So I get 1001. Okay, so by our theorem, this gives me a subgroup. So remember, all I have to do is check that it's not empty, that I have closure, and that I have inverses. Okay, so let's move on to another example. So one important example of a subgroup is what's called the center of a group. So I'll let G be a group, and I define the center to be all the elements A and G, such that AG is equal to GA for all G in my group, right? So these are the elements of my group that commute with every other element of my group. And I call this the center. It's often written as Z of G. Okay, so my first claim is that Z of G is a subgroup of G. So let's prove this. Well, the first thing I need to check is that Z of G is not empty. Well, Z of G is not empty since, well, one thing I know is that EG is equal to G and GE is equal to G. So I know that the identity element is in Z of G. So I know that Z of G is non-empty. And now I have to check closure. So let's do that. I'll say, suppose that A and B are elements of Z of G, right? So then what do I know? I know that AG is equal to GA and BG is equal to GB for all G and G. Okay, so what I need to do is I need to show that AB also commutes with G. So let's do that. So then what do I have? I have A, B, G, right? So AB times G. Let's be careful about parentheses this time. So I need to show that this is the same as G times AB. So what do I do? Well, associativity allows me to move my parentheses. I now know that BG is the same as GB. So I have A times GB. Associativity lets me move my parentheses. So I have AG times B. And I know AG is equal to GA. So this is going to be GA times B. And again, associativity lets me move my parentheses. So I have G times AB. So I've shown that AB times G is the same as G times AB. So thus, I've shown that AB also commutes with all elements of G. So I have that AB is in the center of G. And now finally, we have to check inverses, and inverses are pretty straightforward. So if A is an element of Z of G, then what do I know? I know AG is equal to GA for all G and G. And what am I going to get? Well, I'm going to multiply by A inverse on the left on both sides and on the right on both sides. So this tells me that A inverse times AG A inverse is equal to A inverse times GA times A inverse. And what does this imply? Well, over here, I notice that A inverse and A cancel. And over here, I notice that A and A inverse cancel. So I'm going to end up with EG A inverse is equal to A inverse GE, which is just the same as saying GA inverse is equal to A inverse G. And this is true for all G and G. So this implies that A inverse is an element of Z of G as well. Okay, and we've shown that the center of G is a subgroup. Okay, so what are some examples of centers? Well, one obvious example is that if G is abelian, then every element of G commutes with every other element of G, so that the center of G just ends up being G. Another interesting example would be the center of D4. So these are the symmetries of a square. And what one can check is that well, we know the identity element commutes with everything. So what other elements commute with everything? It turns out the 180-degree rotation commutes with every other symmetry. So that's something to check by writing out a multiplication table. This is kind of a neat exercise if you want some practice with just figuring out what D4 looks like and how it behaves. Finally, the center of GL2 is actually just multiples of the identity matrix, and in particular, non-zero multiples. And this is a really fun exercise. It's worth trying. And then try to generalize it for GLN. The center of GLN is just the non-zero multiples of the identity matrix. So another important example of a subgroup is what's called a cyclic group. So our setting is that G is a group and A is some element of G. And what I want to do is I want to try to figure out what kind of group A generates. What if I consider all possible products of A with itself? So I'm going to call this the cyclic group, and I use this notation for it. So these are all the elements of the form A to the K, where K is an integer. And this is called the cyclic group generated by A. So this is going to be our group. The first thing we need to show, and this is actually quite trivial, is that the cyclic group generated by A is a subgroup of G. So let's prove this. Well, the first thing we know is that A to the 1 is an element of this group. So I know that, or is an element of the set. So I know that the set is not empty. Okay, so that's fine. A is in there. A to any integer power is in there. What about closure? Well, closure is pretty straightforward. I know that if A to the I and A to the J are elements of this group for I and j some integers, then their product, a to the I times a to the j, well, this is a to the I plus j. This is also in my group. Okay, so I have closure because I know I plus j is an integer. And what about inverses? Well, I know that if a to the I is an element of this set, then a to the minus I is also an element of this set, since if I is an integer, minus I is an integer. And moreover, a to the I times a to the minus I is equal to a to the 0, which is e. And similarly, a to the minus I times a to the I is a to the 0, which is equal to e. So I have inverses are in there, right? I'm just showing that a to the minus I is the inverse of a to the I. Okay, so this is a group. So let's look at some examples now. Okay, so let's look at an example of a cyclic group. So I'll consider the group U of Z mod 15. So these are the units in Z mod 15. So these are, again, all the elements of Z mod 15 that are relatively prime to 15. And this is a group under multiplication. And what I'd like to do is I'd like to consider the group generated by 7. So these are all the powers of 7. So this is 7 to the k, where k is in Z. Okay, so let's see if we could figure out what the elements of this group look like. Well, 7 to the 0 is in there, that's 1. 7 to the 1 is in there, so that's 7. 7 squared is in there, so that's 49, and 49 mod 15 is 4. 7 cubed is in there, and 7 cubed mod 15 is 13. And then I'll see that 7 to the 4th is 1, so that's in there as well. And then if I continue computing powers, I'll see 7 to the 5th is 7. 7 to the 6th is 4. 7 to the 7th is 13, and so on and so forth. I might notice 7 to the 8th is 1. 7 to the 9th is 7. 7 to the 10th is 4. 7 to the 11th is 13. And I notice that I just keep cycling through these numbers, 1, 7, 4, 13. If I computed the negative powers, I would get the same set of numbers popping up. So one thing I can reasonably conjecture is that the set I'm looking at here is really just 1, 4, 7, and 13. Okay, but now the question is, how can I prove this, right? The question you might ask is why? Well, what do I know? I know that if k is in Z, so I want to look at 7 to the k. So if k is in Z, I can always write k as 4q plus r, where r is either 0, 1, 2, or 3. So if I look at 7 to the k, this is now just 7 to the 4q plus r, which is 7 to the 4th to the q times 7 to the r. And I know that 7 to the 4th is 1. So I know that any instance I see of 7 to the 4th, I can replace it with a 1. So this is really just 1 to the q times 7 to the r. So this is just going to be, well, 1 to the q is 1. So this is 7 to the r. So I know that 7 to the k, any power of 7, is going to be 7 to the r, where my choices for r are 0, 1, 2, and 3. And then I know that 7 to the 0 is 1, 7 to the 1 is 7, 7 squared is 4, and 7 cubed is 13. So that's how I deduce that this is my whole set. The other thing you might ask is, why is the group called cyclic? Well, it kind of becomes clear because I end up, if the group is finite, I end up just cycling through the same elements. Like notice this pattern, 1, 7, 4, 13, 1, 7, 4, 13, 1, 7, 4, 13. So if the group is finite, I just end up cycling through the same elements over and over and over again. Okay, so let's look at some more examples. So another group I can look at is Z mod 8 under addition. So let's consider, for example, the group generated by 2, and we could do a similar argument to before, but let's see what kind of elements we get. So 0 copies of 2 is 0, 1 copy of 2 is 2, 2 copies of 2 is 2 plus 2, so that's 4, 3 copies of 2 is 2 plus 2 plus 2, which is 6, and then I might notice that 4 copies of 2, so 2 plus 2 plus 2 plus 2 is 0. If I do 5 copies of 2, that's going to be 2. If I do 6 copies of 2, that's going to be 12, which is 4 mod 8. And if I do 7 copies of 2, I'm going to get 14, which is equal to 6 mod 8. And I'll see that I end up cycling through these numbers 0, 2, 4, 6, 0, 2, 4, 6, 0, 2, 4, 6. And what I end up with is this is just the group containing 0, 2, 4, and 6. And this is a subgroup of Z8 under addition. One thing that might be kind of fun to try, exercise, so leave this as an exercise, show that the group generated by 3, so if I take all possible ways of writing 3, 3 plus 3, 3 plus 3 plus 3, so on and so forth, this is actually equal to all of Z mod 8. So it's a fun exercise to try. You'll actually end up producing all of Z mod 8. So Z mod 8 is generated by 3. You can also show the same thing for 5. You could also show the same thing for 7 and for 1. So Z8 is what's going to be called a cyclic group because I'm able to find the generator. So another group I can look at is the group Q star. So remember, this is the non-zero rationals on their multiplication. This forms a group. And I could ask, what's the group generated by 2? Well, the group generated by 2 is going to be 2 to the k, where k is in Z. And I can start listing some of the elements of this group. So I know 1 is in there, that's 2 to the 0. 2 is in there, that's 2 to the 1. 4 is in there, it's 2 squared. 8 is in there, that's 2 cubed, so on and so forth. So I get all these powers of q, but then I also have to include the negative powers of q. So 2 to the minus 1 is 1/2. 2 to the minus 2 is 1/4. 2 to the minus 3 is 1/8, so on and so forth. So this is a subgroup of Q star under multiplication. It's a cyclic subgroup of Q star. Okay, and so finally, we'll look at a few more examples of cyclic groups, and then we'll prove some properties about cyclic groups. So one thing to note is that a lot of the groups that we work with are cyclic. So Z is cyclic. Z is generated by 1. Right? If I want to create the integers, all I have to do is take all the possible ways of adding 1 to itself and the inverse of 1, which is -1, to itself. And I have to include 0 as well. Another group that's cyclic is Z mod n. It's also generated by 1. It's also generated by anything relatively prime to n that's in there, but in particular, it's generated by 1. So I have 1 generates Z mod n. Another group that's cyclic is kind of interesting is the group 1 minus 1 I minus I. This is a group under multiplication. And this is all the powers of I. So this is the group generated by I, and this is a subgroup of C star under multiplication, right? This is the group I to the k, where k is in Z. So this is another example of a cyclic group. Okay, so now we're finally ready to start proving things about cyclic groups. So the first thing we're going to show is that if the order of A is infinite, then the group that A generates is infinite. And if the order of A is equal to n, then the group that A generates contains only a to the 0, a to the 1, all the way up to a to the n minus 1. In particular, it has n elements. So let's go through the details. So the first claim is actually pretty straightforward. So one thing we showed last time was that if the order of A is infinite, then all of the a to the k are distinct. So every a to the k is different from every other a to the k. And what does that mean? Well, that means I have infinitely many elements, right? Because I have one element for every integer. So that finishes the proof of 1. It's pretty straightforward. Okay, so let's prove 2. 2 is a little bit more interesting. And 2 kind of uses the same argument we used in that example with the group generated by 7 a few minutes ago. So suppose that the order of A is equal to n. So what does that mean? That means a to the n is equal to e, and a to the r is not equal to e if r is any number that's bigger than 0 and less than n. Okay, so let's consider a to the k for some k and z. So what do I know? I know by the division algorithm, I could write k as nq plus r, where r is between 0 and n, and q and r are some integers. Okay, so what does that tell me? Well, I know that a to the k can be written as a to the nq plus r, which is a to the n to the q times a to the r. So this is e to the q times a to the r. So this is equal to just e times a to the r, which is a to the r. And what are my choices for r? My choices for r are 0, 1, 2, all the way up to n minus 1. So I can say, hence, a to the k is equal to a to the r for r equaling to 0, 1, 2, so on and so forth. And I know that these are all different from one another, because if a to the I is equal to a to the j, and I and j land in between 0 and n minus 1, then I'm going to have that the order of A ends up being smaller than n, and I run into a contradiction. So what I end up getting is that the group generated by A is actually just a to the 0, a to the 1, all the way up to a to the n minus 1. Okay, so that proves my theorem. Okay, so our next result about cyclic groups is actually pretty interesting as well. It says that any subgroup of a cyclic group is also cyclic. So if H is a subgroup of the group generated by A, then H is also generated by one element. So we have to find that element. Okay, so let's start our proof. If H is just the group containing E, then I know that H is equal to the group generated by E, and I'm done. So what I'm going to do is I'm going to suppose that H is not the group generated by E, right? So what do I know? I know that then A to the I is an element of H for some I not equal to 0. Well, what does that tell me? That tells me that A to the minus I is also an element of H, because if A to the I is an H and H is a group, then its inverse has to be an H as well. Okay, but what does that mean? That means I have A to the I for some positive values of I inside of H. So what I'm going to do is I'm going to take A to the K, where K is the smallest possible power that lives inside of H. So I'm going to say let A to the K be an element of H, where K is bigger than 0 is as small as possible. So this is the smallest power of A that lives inside of H. What I claim is that this power of A actually generates all of H. Okay, so let's prove this. So the first thing that's clear is if A to the K is an H, then every power of A to the K is an H. So the subgroup generated by A to the K is a subset of H. So this much is clear. So now we need to go in the other direction. I need to show that. So now let A to the J be some element of H. What I need to show that A to the J is actually a power of A to the K. So what am I going to do? I need to show that K divides J. So what am I going to do? Well, I know by the division algorithm, I can write J is equal to KQ plus R for some R that's is bigger than or equal to 0 and less than K. Okay, so what does that give me? Well, that tells me that A to the J, this is equal to A to the KQ plus R. This is an element of H. And I know that A to the K in H implies that A to the K to the Q is an H, which implies that A to the KQ is an H. Okay, so now I'm dealing with two elements of H. I'm dealing with this element, A to the KQ plus R, and I'm dealing with this element, A to the KQ. Well, if A to the KQ is in there, then A to the minus KQ is in there. So putting these together, I get A to the KQ plus R times the inverse of A to the KQ, A to the minus KQ. This is an element of H. But what does this tell me? This is A to the KQ plus R minus KQ. This is just A to the R. This is an element of H. But what's the problem? Well, the thing to notice is that R is bigger than or equal to 0 and less than K, and K is as small as possible. So there are no smaller powers of A that live inside of H. So what does that mean? This forces R to be 0. So what do I get? So I could say hence J is equal to KQ. And if I look at this element A to the J, this is A to the KQ, which is A to the K to the Qth power, which is just an element of the group generated by A to the K. So what do I have? I could say hence the group generated by, well, H is a subset of the group generated by A to the K. Okay, so where am I at now? Well, I've basically proved my result. I've shown that H is a subset of the group generated by A to the K, and I know the group generated by A to the K is a subset of H. So thus, H is also cyclic. So H is generated by A to the K. And that proves my theorem. Okay, and our last example of a subgroup is going to be the group generated by not just one element, but by a set of elements. So I'll let S be a subset of G, and we'll assume that S is not empty. And what I'm going to do is I'm going to define this symbol. It's going to be called it's going to be the group generated by S, but it's the set of all possible products in all possible orders of elements of S and their inverses. Okay, so this is how I'm defining my set. And what I claim is that this set is a subgroup of G. So let's prove this. So first, I know that S is non-empty, because if S is non-empty, there exists some element A in S, and so A squared, for example, is an element of S. A is an element of the group generated by S, or the set generated by S. It's going to be a group in a second, but A squared is in there, for example. Okay, let's prove closure, and let's prove inverses. So I know that if A1 times A2 times dot 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 times AK, and B1 times B2 times dot 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 times BJ are elements of this set, so all of the A's are either elements of S or their inverses, and all of the B's are either elements of S or their inverses, well, this implies that A1, A2 up to AK, and then B1, B2 up to BJ is also an element of this set, because what I've done is I've just created a new product of elements of S and their inverses. So closure holds. And then finally, inverses hold, because if I want to take the inverse of an element of this set, well, if I use my properties of group elements, this is going to be AK inverse, AK minus 1 inverse, all the way up to A2 inverse, A1 inverse. I've just created a new product of elements of S and their inverses. So this is in here as well. So this is going to be a subgroup of G. So let's look at a few examples. Okay, so our first example is going to be, I'll let our group be U of Z20. So these are all the elements of Z20 relatively prime to Z mod 20, and it's a group under multiplication, mod 20. And I'm going to consider, I want to consider the group generated by 3 and 11. So let's see what the all possible products of 3 and 11 look like. Well, I know 3 to the 0 is 1. I know 3 to the 1 is 3, so that's going to be in my set. I know 3 squared is 9, so that's going to be in there. I know 3 cubed, that's going to be 27, and then 27 mod 20 is 7. And then I can check that 3 to the 4th, this is 81, this is 1. So my powers of 3 are just going to cycle 1, 3, 9, 7, 1, 3, 9, 7. So it doesn't make sense to take any further powers of 3. I can ask, what about the powers of 11? I know 11 to the 0 is 1. 11 to the 1 is 11. If I take 11 squared, that's 121. That's going to be 1 again. So my powers of 11 are going to cycle 1, 11, 1, 11, 1, 11. So it doesn't make sense to take any more powers of 11. And then I can consider all possible products of 3 and 11. I might notice that 3 times 11 is equal to 13. It's 33, and 33 mod 20 is 13. 3 squared times 11, well, this is equal to 99, and 99 mod 20 is 19. And then 3 cubed times 11, this is equal to 17. And what do I notice from this? Well, the thing that I notice is I've just created all the elements of U of Z20. I have 1 here. I have 3 here. Where's 7? 7 occurs right here. Where's 9? 9 is right here. Where's 11? 11 is right there. Where's 13? 13 occurs right there. 17 is right there. And I notice 19 is right there. So it turns out that the group generated by S is all of U of Z20. So it's kind of interesting, because the group that S generates, I only need 2 elements to generate all of Z mod 20. I could change this example just a little bit now and consider maybe the group generated by 9 and 11. And let's see what we get. Well, 9 to the 0 is 1, so that's going to be in there. 9 to the 1 is 9, so that's going to be in there. 9 squared is 81, which is 1, so that's going to be in there. But now it doesn't make sense to take any more powers of 9, because I'm just going to see 1, 9, 1, 9, 1, 9 over and over. 11 to the 0 is 1. 11 to the 1 is 11. And we saw before 11 squared was equal to 1. Okay, so those are all the powers. I'm going to have a 1, a 9, and 11 in my set. And then what else can I do? I can do 9 to the 1 times 11 to the 1. That's the only other power I can create, because 9 squared becomes 1, 11 squared becomes 1. So the last thing I can do is 9 times 11, and 9 times 11 is 99, which is equal to 19. And those are all the powers I can do, because if I hit 9 squared, so 9 squared times 11 is going to be 1 times 11, which is 11. If I do 9 times 11 squared, that's 9 times 1, so that's 9. And I've run out of options. So I see that the group here, generated by S in this case, is just going to contain 1, 9, 11, and 19. And I'm done. Finally, in our last example, we'll consider the group D3. So these are the symmetries of the triangle. It's a dihedral group of order 6. And I'll consider the set S containing these two elements, R120 and V. So the 120-degree rotation and the vertical reflection. So let's see what elements these two generate. So I know R to the 120 to the 0, this is R0. So that's my identity. R120 to the 1, that's R120. If I take R120 and apply it twice, I get a 240-degree rotation. So it's R240. And I might notice that V times V, so like V to the 0 is R0, V to the 1 is V, V squared, if I apply V twice, I get R0, because remember, any reflection inverts itself. If I perform the same reflection twice, I just got back to where I started. So I might ask, well, what if I combine R120 and V? So if I combine R120 and V, I end up with D2. If I combine V with R120, I end up with D1. And then I might ask myself, well, wait a second, I think I've just created my whole group, right? R0 is here, R120 is here, R240 is here, V is here, D1 occurs here, and D2 occurs here. So the thing that I might notice about D3 can actually just be generated by two elements. D3 can just be generated by a 120-degree rotation and a reflection. So this is kind of neat because I can show that if I want to capture all possible symmetries of a triangle, all I need to have is one rotation and one reflection, and I can write every other symmetry in terms of those two. And this is actually true for all dihedral groups. So any dihedral group, if I have a certain rotation and one of my reflections, then I can generate the entire group. So I want to, in particular, pick the rotation of that gives me the smallest degree angle. So if it's an n-gon, I want to use 360 over n degrees.